Easy. Good afternoon again, all. I will keep it very short because the first two speakers have about 50 slides each. So I'm going to be brutal to stop them when they have reached their time limit, but since they are a little bit, how would I say, not so well in following my instructions, I hope that you will help me. So if they keep continuing, start booing or something like that. Without further ado, I give you Lina Wadia, who is going to tell you about the wireless LAN deployment at CERN in Geneva. Lina.
Thank you, Klaas. Can you hear me? I'm usually a loudspeaker. But I have a problem, which is that I tend to speak very fast. So if I'm doing that, please put your hands up or do something if you want me to slow down. Okay? It's hard to give talks on wireless because many people know many things about it. I'm going to start my talk at slide 5. I left the others in because it was meant to be on the web and I wanted the presentation to be complete. So the wireless requirements at CERN, there are about 430 buildings at CERN spread over 2 sites. And we estimated that we need anything between 3,000 and 6,000 access points. But only 200 of those are installed. So by no stretch of imagination is this a large wireless deployment. But we've learned a lot in the process, and I thought it would be a good idea to share some of these with you. Because at CERN we get the opportunity to install these things in very strange places like the underground LHC tunnel and the experimental pits, and then equipment testing halls where there are very fine magnetic fields being tested and wireless would disturb and so on. So it's been fun actually doing this. So this talk is really about experience sharing. I mean, what have we learned so far? When we began, we wondered whether we need A at all, because A was 802.11a was late coming to Europe, and then we were wondering whether we need it at all. And then for BG, how should we do the deployment? Should we use large cells, small cells? What kind of hardware properties should we be looking for? And all those kinds of questions. So this is what I'm going to share with you. And the basis for the knowledge that I have is some of these unusual installations that we've done. And I will talk to you about them as we go along. Now, Klaas is our chair, and he is the person pushing security, and he's very devastated that I'm not going to say much about security at all, but I will have one slide on security to keep him happy, actually. So before we begin, just to remind ourselves that we are talking about wireless LANs that are based on the 802.11 standard, which are in the unlicensed bands of 2.4 gigahertz and 5 gigahertz. 5 gigahertz has a lot of bandwidth depending on which part of the world you are. In Europe, this part is more or less available in all countries. So the 2.5 gigahertz band is the BG network, which everybody is familiar with, and the 802.11a is going to be the 5 gigahertz band. The 2.4 gigahertz band is kind of crowded because it has cordless phones and Bluetooth and whatever, and the 5 gigahertz band was late in being released, especially in Europe, because it's used a lot for defense, and I'll come back to that point later. So just a quick picture of the standard. The 802.11 family of standards is still evolving. The original standard was the B, the Wi-Fi that we know, which had first 1 and 2 megabits and then 5 and 11. And then they made a very big breakthrough in modulation, and they did OFDM, and they got bandwidths of the order of 54 megabits. That was 802.11a, but it was blocked in Europe. And then they came the G, actually. So this is the main standard. It covers the physical and the MAC layer. And then, of course, the standards have been evolving in many directions. One that is important to Europe is this 802.11h compliance, which basically says that if an access point senses that there is a wireless signal in the 5 gigahertz band nearby, it has to switch to a region of the 5 gigahertz band. So there are two things: dynamic frequency selection. Where's my mouse? Yeah, dynamic frequency selection and transmit power control, and this is meant for wireless installations in the unlicensed band to avoid defense installations. So until access points, complying with this standard came on, they couldn't really be deployed. And then, of course, there's lots of the 802.11i, which is complete, which is a security standard. And then there's inter-access point protocol for helping roaming and mobility and so on, but I won't get into all that, okay? So the BG, I will say very little. We all know a lot about it. The most important thing is that at CERN, and like everywhere else, I don't think we have any choice except to install BG access points in the BG compatibility mode, because there are still a lot of people who have 802.11b only cards, which are low speed cards, and what that does is that reduce the available bandwidth in a multi-user scenario to something like 14 megabits that you have. And of course, the BG has another problem, that the 2.4 gigahertz band is only 80 megahertz wide. So that means there are only 3 non-overlapping channels. So, you have really difficulties with installation. I'll show you that. So here's an example of some signal measurements that we did in a building in CERN. It's building 28 on the main floor. So this is a tool that we have, which is a surveyor tool from Air Magnet. What we normally do is simply install an access point where we want it, and then go around with this tool to measure the signals. And what we see here is that these are load-bearing walls, and they are concrete. And what we see here is that the signals actually go to only about, they really cover only two sets of offices on either side of the corridor very well. So this is really an example of a bad installation. People here, of course, in this picture, if you look at the scale, the green areas are acceptable signals, and the yellows are bad, and the blues, of course, you'll never get them. But here it looks like it's yellow, and here also that you can work, but people in these offices really cannot work. So this access point is serving only about 4 rooms. So putting it in the corridor was a bad idea. And one of the ways that we could see that it was a bad idea was to watch the parameters of your network. And one of the parameters that the interface card gives you is how many frame check sequence errors you have. And there were 30 million transmitted frames and 52 million frame check sequence errors. So this is bad, okay? So what we discovered at CERN is that the buildings are old, and they have lots of concrete and so on, and there's really lots of sources of noise and absorption. But there were some which even I didn't know, that, for example, tinted glass, colored glass actually tends to keep the signal inside the building, which is actually a help. Plain glass sends it all out. So in the previous thing you saw that these were plain glass windows, and the signal simply spilt out of the windows. So what happens is, from the access point, the signal moves out, bounces around a bit, gets in through the doors, and then simply goes out of the windows. So with three non-overlapping channels, you can see that I've tried to make them 3 different colors. I hope it's clear to you that if you are tiling space in 2 dimensions, 3 colors are okay. But as soon as you start going into 3D, you need more colors in order to have one colored ball surrounded by all kinds of different colors. So this doesn't work in BG at all, and we have plenty of problems with noise and so on. And typically we see numbers like 20 decibel for noise in many, many buildings actually. So this is just a schematic picture of how bandwidth falls off with distance. The rate at which your wireless card can communicate with the access point falls off with distance. So it's a schematic. So don't believe the numbers too much. But basically, this brings in the question that should we be having small cells or large cells? And in the beginning, I was a big advocate of having small cells because I felt that you needed to have the bandwidth actually. But we've become wiser over time, and we've realized that there are many situations where you need to have very large cells where anyway there are few users, and the coverage situation is such that there's a lot of overlap. If you have a building, I have a picture later, if you have a building with a long corridor and several floors high and glass floors, then the signals from upstairs and downstairs all tend to merge, and they create a lot of noise. So it's better then to have large cells. But I'll show you an example of one situation where we did small cells. And the other problem with this is, whether you should have large and small cells, is that at one conference like this, in a room like this, where 90 people could be sitting, we had 90 scientists, and 55 of them were online, and we had over 30% retransmissions. That, by any definition, is a bad network. So, This slide I just put it in here to say that, by and large, wireless usage at CERN is still very sporadic and very little. You see, what's the point in installing an access point with megabits capacity if you're going to use something like kilobits? It's sporadic and small usage in many places at CERN, because CERN is actually wired very well. There's a lot of wired outlets, so wireless is only supplementary. If you're using wireless to replace wired, then it's a different ball game altogether. Then you have to make sure that everybody gets high bandwidth transmissions. So the thing I wanted to say about A is that A has a very big advantage, which is that it has many more non-overlapping channels, which means that the adjacent access points in a building will not interfere with each other too much. But it also has a natural disadvantage in the sense that the 5 gigahertz band has a smaller wavelength and so lower range. But we have found in real life that the 5 gigahertz compares very well with BG. First of all, because it's not subjected to noise, and secondly, because if you have good quality radios, then they compensate for range actually. So some things we learnt about A I wanted to share with you. This is a picture of a casino Kursal in Interlaken, where we organized CHEP, Computing in High Energy Physics 2004. And what you see here is a picture of the signal actually. It's mostly green, but partly this room is the main room where we had the plenaries, and we couldn't walk in there, so we couldn't sample very well. So it's not very green, but it was really like this everywhere, But like this conference, it had 500 plus attendees and 300 plus laptops, and at least 200 were connected at any one point. And what we saw was very interesting, that we felt that people should have very high quality bandwidth, so we installed 10 access points in this room, so that people would have, if there were 300 laptops, people would have there would be about 30 people to a laptop, to an access point. But we found that at one point, 220 people were online, and more than 170 of them were being served just by these 3 BG access points. Because we had set SSID CERN for all of them, and everybody has typically, what is called smart selection enabled on their card. The card picks up the strongest signal and connects. Now, at any point if there's an access point on the roof, at any point from there, the BG signal is always stronger than the A. And so your card naturally connects to the B channel rather than to the A channel. And this was a very important lesson to us. As a result of that, what we have decided is that we will have separate SSIDs for the A and BG network. So if you go to CERN now, you will have a CERN and a CERN A. And we encourage people then to use the A network, because the A network has better bandwidth and less interference problems. So at CERN, we are installing dual band access points. And there's one very peculiar problem that is relevant for A's in Europe. Because of this requirement that you cannot specify a channel in the A band, you cannot say, when you configure an access point, you cannot say that it should be channel 36 or channel 40, because it has to sense and move away from existing signals. What happens when there's a power outage and all the access points boot together, the access points seem to be checking for signals only once. And then we find that there are 3 or 4 which are in the same, nearby ones which are in the same channel. And the only way to solve that problem is to reboot each of them individually in a staggered way. It's a bit stupid, but it happens, and I'm sure some of you have noticed it actually. So this is so basically, what I wanted to say was that we at CERN found that it was a good idea to have feature-rich access points, because we have to install in strange places. For example, wireless distribution system. Typically, you might not feel the need to have it. If you have a building which has several Ethernet access, ports on the wall, then you just plug an access point in and you're okay. But I will show you an example of where we needed the wireless distribution system. We use power over Ethernet heavily, and we also use the rogue access point detection support heavily. I will just show you in a minute. And It's very interesting. If you survey the products that are available on the market, very, very few of them will actually transmit at 20 dB. You know, if you check, that means that most of the access points in the market are not transmitting at full transmit power, which is 100 milliwatts. If it goes to 17 dBm, it's already 50 milliwatts. So it pays to look for good quality hardware, and we've done that. And we are also asking for WPA2 and 802.11i compliance. This is a picture I have of taken from, again, an air magnet tool, which is a laptop analyzer. And what you see here is what would formally be defined as rogue access points. If you look at these are the ones labeled CERN are official installations. And we have at least as many which are not official CERN installations. But we are tolerating them now because we really are very slow with installing wireless. We don't have the manpower to do it. And provided they are well configured, they are not doing DHCP, we leave them alone. But you can see here also an example of a badly configured access point. And then these guys, we have to actually go and look for them and shut them down. And recently we've written a piece of code that actually takes the rogue access point reporting from our access points and turns them into an alarm on our network management screens. So I have now only some few pictures of installations at interesting installations at CERN. So let me just skip this slide and just before I skip this slide, let me just show you this picture. This is a building where we did our first full installation. We wanted full coverage. Those of you who've been to CERN will recognize that this is Hostel 39, where people come to stay, and the Americans want to start working when the Europeans are going to bed, and they didn't have any connectivity. And so what I will show you is a measurement that I did of coverage on the first floor. Please notice this tinted glass here, and then you'll see. So here's the coverage that we measured of the installation. We had 4 access points on each floor, actually. And if you look at this scale, the signal to noise ratio, we are in very good numbers. Near the access point, you get something like 70 dB, which is actually a very, very good installation. But what is even more interesting to see is that where there is tinted glass, the signal does not spill outside. And you know these things, but they don't hit you until you actually look at a picture. And this is also an example of a successful installation with small cells. So here's the placement of cells that we did. It's really, I mean, all of them had different numbers. This was successful because we didn't have, for example, elevator shafts or shafts running through the building which were carrying pipes and so on. Because if they do that, then the signal gets in there and then goes downstairs and upstairs and so on, and it messes up. But this was a successful small installation. This is the Alexei tunnel. This is my colleague. He's making some measurements. This is a power box, but what you see here is the VDSL connection. You can't use Ethernet in the tunnel because the distances are several hundred meters long. So they are running VDSL on Cat6 cabling, and what we were doing was to see whether the signal propagates enough in the empty tunnel and in the full tunnel for people to work, actually. So this is an example of a full tunnel. There's somebody welding here, and these people, very often not the welder, but other people need access to the network, and we need to measure. And it was very interesting. The coverage, there's so much metal around here, but it just bounces all around, and the coverage is excellent in the tunnel. But in the tunnel, we also discovered something else, which is that there was one section of the tunnel wall that was wet because the tunnel is leaking, and then the wet wall, it acts like a complete suction. It just pulls all the signal in, and the signal never crosses across. That was really something spectacular to see. Another idea we got from the tunnel is that what you see on the wall, that this is the optical fiber, and here we have a leaky feeder cable for GSM. So we got the idea that why don't we try to use, in these long, heavy concrete buildings, why don't we try to use leaky feeder cable as antenna for wireless? So we got a company to mail us leaky feeder cables in the 2.4 gigahertz band, and we tested it, okay? So I'll come back to this slide later and look at this. So this is about what we got. This slide, yes. This slide is, we got from the company. But if you look at this, the scales are inverse. Normally the yellows, in the pictures I made, the yellows are down here and the blues are there. But what you can see is that this green portion, which you would like to have, there's very little of it simply on the corridor. And everywhere else, the signal is very, very poor, actually. So the first results are not promising, but we haven't given up on it. We could try to use an amplifier, or maybe the coupling of the antenna. The antenna on the access point and the leaky feeder cable is very resistive, but we're going to give it a shot, because if it works, it's very, very useful way of covering all these rooms in a hostel. And here's an example of what I told you about where needing, wireless distribution system. The people working here often have calibrations to do and data to send to the network. So this is a large cavern, 50 meters by 30 meters or something. And we have one access point here, and we have another one here. This is the only one that on this wall. It's behind the green screen, unfortunately, so you can't see it. But this is the only one that had Ethernet connectivity. And then we had a third one down here on the floor of the cavern. And then so long as these three access points are within line of sight of each other, then only one of them needs to have an Ethernet connection, and they share it, and it works beautifully, actually. So if you've been to the Atlas cavern, you would have seen it. Security, we are very much behind in security. We have, at the moment, a completely open network. We don't use encryption. The only precautions we have is that we have a registration process, so that if there is a problem, we can eventually trace it to somebody. So that's all. And then we try to encourage people to use safe applications in quote, meaning applications in which passwords are encrypted, actually. In the short-term future, we are right now testing and working on the database changes for introducing radius for authentication. And we decided that we won't do it only for wireless network. We will do it for wired as well as wireless network. But then the challenge at CERN is that you have devices like PLCs and VME crates and all kinds of things which cannot do certificates and so on. So we have to come up with a solution that matches everybody. So the last word really is that I can skip this. Wireless, as we all know, is not even as good as shared Ethernet, but people seem to like it very much. It's convenient and fun. So they're very tolerant of poor performance, bad connections. At least people at CERN are not complaining. And the usage levels are still low and sporadic. But it's my personal viewpoint that right now the technology is not mature enough. There's just far too much manual adjustments that we have to do in terms of performance tuning and load balancing and failure compensation and so on. So this is the real dream which wireless switching is promising, that if you have a bunch of cells and one cell becomes very overloaded because there are a lot of people there, then the cells would adjust themselves in size so that all the people on the edge of this thing will get attached to neighboring access points. And similarly, if there's a failed access point, you would have the cells adjusting in size using transmit power control so that the coverage is complete. So this is the promise of wireless switching, but it's a long way away. It will, because there's not yet a ready standard governing it. I think people are working on standards, but it's a long way away. Some years for sure. So I'll stop here. Thank you.
Thank you, Lina. I was a little bit worried that she didn't breathe at all, but she managed okay.
But that's my normal state of affairs. I'm always speaking that fast.
And we even have room for one or two questions, if there are any. Over there in the front.
About this about these wireless switches, there are some proprietary solutions, for example, Tricom. Are you never consider proprietary solutions, or?
No. It's a CERN policy to use all standards-based, because we are a multi-vendor site. We have routers from every vendor, we have switches from every vendor, so we can't afford to do that, because we'll buy hardware and grade it, so they all have to interoperate. So it's.
Okay.
Do you have any vendor of access points that you would recommend for large wireless LAN deployment?
I think that's a dangerous question. But we started with the Proxim AP2000, And then we moved over into an AP4000 because that does the A and the BG, and we are really happy with it. Yeah. But yeah, we did it on a tender process, and then we specified what we wanted. But it is true that the Proxim boxes had certain functionality way ahead of many others. So that's how we got them.
Well, since there are no other questions, I would like to thank again Lina and ask the next speaker to come up. Our next speaker, many of you may have seen him already last year when he came in via video conference all the way from Tennessee. This year we have him live, Philippe Ancet. I was taught only in the break to pronounce the name. Apart from running one of the largest wireless networks in the world probably, at least in the educational environment, Philippe is also the chair of the FWNA group, the Federated Wireless Network Access Group, and, well, in short, you could say EduRoam US. And Philippe will share with us some of his experience in the wireless LAN area. Philippe.
Thank you, Klaas. Good afternoon, welcome. I'll try not to be as fast as Lina. So, yeah, that's one of these favorite pictures of our campus. I've never seen it that way, except if you go in an airplane. From my office, it looks a lot less nice. We have, but the population is quite nice. 26,000 students, 4,000 faculty and staff. You see the number of access points. We started with 200 users in 2000. We now have 14,000 registered users, and so 1,500 on a daily basis concurrent users, and about 2,000 daily. There is something. How do you get full screen here, Klaas? I don't speak Polish, yes. Dziękuję. For sure. So I'll immediately jump into the topic. We got lucky. We got a centralized deployment. The IT office is a dictatorship. We tell people what they should do or what they should use. And so, but in the case of wireless, it happened to be very convenient. We decided immediately to have a gigantic layer 2 network, so people can roam as they wish. The RF was well integrated. You don't have to deal with a neighbor building that has decided to use channel 6 and you use channel 6 as well. You end up with all these interference. We have a centralized registration system that we wrote ourselves. In 2000, there were not too many of these boxes that would do it for you. Also, very convenient, one phone number to complain, and our response time is usually pretty good. I mean, that's me saying that, of course, as the users, that's another story. And but even though I say we are an IT dictatorship, we do allow exceptions. Actually, it's not a dictatorship at all. We work a lot with users when they need special applications, because wireless is not only about laptops. We have many exceptions. People have FBI grants and they need a complete secure environment, so we work with them for them to have their wireless network. Another one is these robots. Originally, that scientist had a frequency hopping wireless network, and so we work with her to have the frequency hopping working with the distributed DSS spectrum. Sorry. But on the discussion lists, you see a lot of people dealing with decentralized deployment, and I'd like to remind everyone about some of the inconvenience of it. And they often happen by accident. People start, computer science is an innovator, they have a wireless network, then the business school. And so it usually works okay if you don't have buildings next to each other, but people tend to forget that a window can have an access point a lot stronger from another building than from the building itself. So you end up with this nightmare. So there is no such thing as roaming, of course. Which phone number do you call exactly when you have a problem? The security, good luck, unless EduRoam comes up, and then people will standardize, of course. But it can lead to very interesting developments. University of Utah, actually, I believe, if I'm not wrong, that EduRoam got inspired by the University of Utah case, where they had a bunch of departments, and they decided to go with 802.1x. And the only solution they found was to actually make a roaming of radius. It's a local roaming radius community. Chris Hessing there is the one who developed Open1x. And so they are it's a sad case where actually it came up with a very nice technology to solve that inconvenient story. And by the way, if you don't have a centralized one, the only thing I found to be useful is to get a CIO on steroids, an acceptable usage policy, and an attractive cost model. And speaking of which cost model, ours is free. We made it that way originally. We actually take a little bit of money from the wired network. We take $1 for every port that is being paid for wireless. And it works very well. It also prevents a lot of rogue access points condition. But what we see, and I will move to the management tool, is that people tend to like wireless, and they don't like to pay for wired. And with 802.11g, well, you get a decent speed, and if you're in an isolated place of the building, you're almost alone on the access point. So why pay for wired? You just joined wireless. So we are starting to see cases of permanently connected people with desktops on wireless. So the cost model, the free cost model, is not always perfect, unless you provide free wired infrastructure and you find a way to centrally fund that. So like I said, the free wireless minimizes the rogue access points, and also it's easy to say, but full coverage and free coverage literally diminishes the rogue APs to nothing. Why would you bring and buy your own access points if everything is provided to you? Because of these happenings, we do monitor actively the usage, and we developed our own tool that I will show you soon. If you charge, well, that's for you, but not for me. The management of this, the accounting that we have been exploring a way to charge for it, but we immediately gave up. It reminded me of the remark of this morning. It seems like a stupid idea. Of course, you can imagine to subcontract with a T-Mobile of the world and having agreements so that your users that are you get it from T-Mobile, your campus managed by T-Mobile. When you go to airports and hotspots, you get free roaming. But supposedly, EduPass will solve that. So, also good luck with rogues. As soon as you charge, I don't know, 25, 30 euros, you get an access point, and there you go. So, and also if you charge, how will you charge? Per bandwidth, per access? So I made a little prank there. The last item was, we call it Internet 2. People create Internet 2 because Internet 1 was starting to be very commercial. Maybe we'll have to create a WLAN 2 for wireless research networks only. So how do we control the access? I will show actually an overview of the different way to control access these days. This control approach, the aggregated APs with controller, has disappeared, I believe. You can still buy those, but those were the early days where they were requesting you to have a switch from the vendor with a port per AP, and the switch was completely controlling the access point, but you were requested to have one port per AP. then they realized that the distribution of this was impossible. They created 20 switch ports, and most of us have 3 or 4 access points in an equipment room, so you pay 20 ports and you use 3 of them. It was a complete unfeasible business plan. Of course, the controller takes care of the registration. You don't have to write all that. Lots of features, but an inline technology. These switches, they may call them switches. If you've noticed, they are often PCs with a lot of Ethernet cards inside. And I don't know about you, but it took us about 10 years to have a stable network with stable switches vendor. I don't want to go to these buggy developments where I receive pages all the time about device being down. So I'm not keen at all on inline technology these days, unless they can prove that they are very reliable. So the way vendors have adapted to that is by providing still a controller system, but with a tunnel technology. So you need to buy the proprietary access points, and you end up with a controller that can be remote from the place. Basically, you have your choice of, that's why the second item here, not forced to use vendor port for AP. You can use your own power over Ethernet, and then there is a GRE tunnel, proprietary tunnel that talks all the way to the controller. That's actually pretty nice. If you don't pay attention, and if you start to end up you enable a lot of these tunnels, because some of these vendors limit the number of tunnels to 200, 100, depending on the bandwidth, you may end up with building a pretty nice dish of spaghetti there. You cross these tunnels all over you. It's layer 3, so you can really do whatever you want with these things. Again, the controller takes care of your authentication. It's very nice. Lots of features. But then again, inline technology. It's a PC with a buggy code, or maybe not buggy, but I'd rather have you discover it than me. And how will it sustain the new standards? The idea of 802.11n is that you will have a net throughput of 100 megabits per second. Well, that's, imagine 100 access points on this. That's a lot of bandwidth for a little PC box. How will it grow? That's the next question I'd like to ask to these vendors. So you may have heard already many times, I'm not too keen on inline devices. So we decided to really, that's the last one, the blue socket of the world, and Vernier, etc. You don't need an access points from them. They are basically gateways, and these gateways can be in many places on your campus. You can be as close as next to the access point, or all the way just for the authentication. Again, you can do traffic control. A lot of them have a fairly decent way to do IP mobility. Sorry to mention that again, it's an inline device. Did I mention that? And also, if you have a lot of subnets, unlike the tunnel technology, well, you have to put one of these gateways for every subnet. For instance, Harvard has 40 blue socket boxes. And I don't want to manage 40 blue socket boxes. And back to the same question. How many of these boxes will you need when you have 802.11n full-blown connections going through these boxes and you upgrade your access points? So we developed a tool on our own. I call it the Octopus Design because I always picture this big head and a lot of arms, about 8, controlling all these functionalities that you already have on your network. Your switches have access lists. Your access points have usually a fairly decent set of features. You have your ARP tables, you have your routers, you have so many things that you can question that will give you a lot of the information that, let's say, a blue socket box, a gateway, is actually doing in a box. They do it in a box because it's convenient for you. But if you can write the software to question all these boxes remotely, you can actually stay offline and do a job that is maybe not as powerful because you cannot stop the traffic as you wish, but I'll talk about that. But you can do maybe 90% of what these gateways do. So the idea is to use what we already have. The tool is called Swingle, Simple Wireless Network Governor. So we do an analysis where we prevent IP spoofing. And in the case of 802.1x, it's still a fairly useful thing. 802.1x, look, you end up like, okay, now everything is secure, encrypted. It looks very crunchy on the outside, but it's still juicy on the inside. That doesn't prevent people from creating a huge amount of bandwidth. It doesn't prevent them from, like I said, being permanently connected with a desktop machine. Desktop machine do 802.1x. So monitoring and IP spoofing, all these things are still there. 802.1x does not alleviate that. So we monitor the routers, the access points, and at the moment we are doing MAC address authentication. We hope that 802.1x MAC address is here, and 802.1x will progressively replace that, so that we can just have MAC address authentication for like those little robots I showed. You cannot expect any device to have 802.1x anytime soon, at least. So maybe in the future it will be like that. We are not doing that yet, but we will use accounting from radius to also correlate these events. So Swingle, I was telling you, I'm not in line, so I don't have too much power to block people, etc. Well, we are not doing that yet, but I think we could. What prevents that Octopus architecture, that boxes on the side offline, to control actually the access list of those switches you bought that you paid quite a bit for it? And when you use a gateway, you often don't use the features of these layer 3 switches if you have them. So the idea would be Swingle not only to monitor, but also to become an active part where you get the information and you do a reaction based on that. There may be a delay that the gateway have, but so there is a trade-off to every technology. You can put MAC filters on access point. You can put you can change your firewall rules, and also with 802.1x control your radius sessions. So let me show you. Also, one thing I forgot. With this idea, of course, of controlling everything like that, you end up in need of a lot of the features from the access point, which is the VLAN per SSID. So we extensively use SSIDs. It may sound like an SSID nightmare there, but I don't think you will use more than two, a registration one and then the one you use on a permanent basis. So the moment you see all these, maybe eventually the eduroam one will be the only one. We still would like to keep an SSID for visitors. We open our libraries to the public. Why not open our wireless networks to the public? It seems, you go to the library, you want to check the catalog online, and all the desktops are occupied. Why not use your laptop? If you're a visitor and you're not even related to the education community, you're still entitled to go to the public library. It's a state-funded infrastructure, so we are forced to allow people. So I think we will keep a visitor network for that purpose. But very limited, probably, just email. Basically, the campus is here, and people will just pass by the network to be able to check their email and things like that. So, yeah, of course, you do a juggling of SSID, but my hope is that we are not doing that yet, but we would like to do that. What some vendors do is that you do an 802.1x here to 802.1q mapping. So your VLAN, the access point is really the one taking care of that. Your 1x session is resolved to a VLAN. It's not anymore over the air. It's only, you have maybe one or two SSIDs and that's it. The rest is being taken care by your users may have definitions in LDAP. You belong to the faculty VLAN or you belong to the student VLAN, etc. So that's the tool, Swingle. You can see here 1,210 APs. Oh, well, we missed a few, I guess, in the monitoring software, or maybe I overestimated the number of APs we have. 14,000 users. We constantly monitor the bandwidth. We have a few dead APs. I need to call them about that. It's not real time, so hopefully it's solved. So that's what we call the knock page. You take a look, you immediately see, okay, what's the utilization? You see that people come around 7, they leave around 7, so 12 hours of active usage there. I will not go into the details of the software, but you see here this admin button. We can control all our access points from there. Upload the code. We can upgrade. We have groups of groups. We put in that software everything we did not like in the commercial softwares that was inconvenient. Like paging, well, you can pretty much go to the granular level where you can enable paging for every access point and for a number of people, because sometimes, back to that IT dictatorship that we have, like I said, if someone in the computer science department would like to know about an access point going down because they rely heavily on these, well, I don't mind putting their name on the paging so that and we do paging on email, on regular pagers, you name it. You can plug your script to it so that paging triggers a script and then the script does an action. I will mostly talk about the monitoring right now. So if you look, I will simulate an active usage of the software. If you go to that first MAC address here on the top bandwidth users, I click on it, and then I get a graph of the utilization of that user. What we do is through SNMP, we pull all our access points. Right now, we do it on a 5 minutes delay. We could do it on any delay we want. It's a matter of how much the access points is being bothered by that constant monitoring. So, we went with 5 minutes for us, a good safety limit there. And you see that user is always on WDE23. It's a wireless Doherty building, 2nd floor, 3rd AP. We can check their signal strength. So in the future, what we would like to do with the collection of data is even help the folks on the help desk use those signal strength to see if there are any anomalies. If someone complains about the wireless network, is it really the wireless network or is it maybe their card? If we see that they're constantly connected and they have drops in their signals to noise ratio, we could do a summary of that. And so people at the help desk can see reports and see and maybe call back the users and say, listen, why don't you bring your laptop? I think your infrastructure is pretty okay. So that's the top of the graph, and then the bottom. We also, in the idea of correlating everything in the Octopus idea, we immediately resolve this to the registration database. And if you look, of course, for privacy reason, I hide it. But it would have been a nice permission for that guy to be showed to everyone. We correlate that with the LDAP. And so we can immediately have, if you click on the IP address, we also, you get the lease. So we know for how long, if it's a valid lease, for how long is the lease available. If we go back to the main one, and we go to top bandwidth APs, actually you see that there is a good correlation here. WDE23, the top one. Can you read this? Oh, okay. The top one is WDE23, and it's actually the one that was being used by the top user here. So it's good for the software. We are not completely off guard there. We click on the access point, and we get all the users that the traffic for for the last 24 hours. And you see that the 00904 ending with C016 is that it's the same user I was showing you on the other the user graph. Then we go back to the software, and we found some interesting happenings thanks to this monitoring software. If you could do line here, 1415, where I put you can see the little hand? Yes. Yes, the little hand is, there you go. Now you see me, no you don't. It's about here. So I'll click on this one and end up with this. Well, we were wondering for a long time, this user was creating an incredible amount of data and very constant. It's Axis. It's a video monitoring camera. They decided to bypass the cost model and use wireless. But you know, honestly, these days, you have to order a power circuit for the video camera. So it's cheaper to order power over Ethernet and even get data for free. So I need to go talk to these folks and say, listen, your little bypass of the cost model is ridiculous. You need to pay me and stop paying for electricity. 2 minutes, okay. So roaming models. I call that vertical subnetting versus horizontal subnetting. With that gigantic layer 2 network, we did have a lot of broadcast problem. So now we decided we need to segregate that. So first we looked at how we could split horizontally, pockets of wireless. And the campus is so compact, we would have ended up with the problem I was mentioning to you. No IP roaming, because you would have the signal from another office, and you would move up, get on another subnet. So we decided to do vertical subnetting. So we used to have one gigantic layer 2. Well, we just increased the number of SSIDs. And that's where 802.1q, 802.1x to 802.1q comes handy. You will have all the faculty in one network and all the students in one network, or maybe the young students in one network, the older students in another network. We can segregate by age or whatever. Maybe by the 24 digits of the MAC address. We'll have to find a way to segregate there. But so it's really building a vertical subnetting like that. So you still accomplish roaming for that class of user. Rogue device detection, it's building the access points. So for the wired side, so we do it on the UI first, of course. That doesn't work too well. Too many vendors have different UIs on the wireless and on the wired. So fingerprinting works pretty well. You can detect, the HTML signature of some vendors like Linksys, etc. Some people propose the time to live, because many NAT boxes have a different time to live on the packet that leaves the network than Windows does. So it's a good hint on if you have a NAT, or often it's a wireless access point. To give you an example about wireless is free, it gives you it prevents rogue APs. In our dormitories, we decided not to provide wireless, where we have about 200 rogue APs there. So we decided to fund this and probably provide wireless. So that's a nice thing. The last item here on network registration is doing. We have this very pervasive executable that runs on your machine to check your patch level, collects the MAC address of your Ethernet and of your wireless, brings it back to a server. But also when you got your lease from us, we got your MAC address. Well, we did a check of these just to make sure that we have the right person. And of course, when you have a NAT box, they never match. So we detect NAT boxes just by a side effect of a registration software, which is quite convenient. Wireless side, so we have that on the wireless access point. We do like Lina. We receive a trap. We compare that to our list of MAC address, see if it's a friend. But also we keep on doing that because even friends, we check to see if we see all our friends. We are using Rogue AP for also quality assurance. An access point has 3 neighbors and detects 3 neighbors. If one disappears, well, if it's a friend, it's basically one of our radio that died. So we use Rogue AP detection for quality assurance, and because not many access points, I don't think it's even possible, have a trap that sends you dead radio. It's like us saying like, oh, I'm dead. There is a catch-22 problem there. And that's my frustration. You live in Tennessee. All the technicians use these huge V8s van to go check access points. So I wish we had a Segway and have people going there for because that's really, it boils down to that. When you have a true problem, you end up going on the field anyway. Adhoc is a major problem. The detection, one day we were in an auditorium like this with access points, and there were 5 Adhocs. There's no way to detect that. I can aim my radio there. It might be you. It might be you. So the remediation we do is that we would like next semester to push on the Windows and Mac to disable it's very easy. It's in the advanced settings. You just push that. You push the radio button, and you force people to only go in infrastructure mode and not on ad hoc. Special projects, I'd love to put all the network on uninterruptible power source, because if you realize you are uninterruptible power source, so it would be really nice to have the whole chain on uninterruptible power source. The whole network shuts down and everyone on wireless is fine surfing the internet. That would be very nice, but it's a bit expensive. APs on solar panel, we use that. We have done one experiment and we discovered the same with the tinted windows. I thought I was smart. I just put the antenna, my 5.8 gigahertz antenna on the window, and I had zero connectivity. I'm like, what's wrong with this antenna? And then it was the window, of course. We also monitor cows with Wi-Fi. Well, you know, if you look at proprietary solution, they cost like $1,000 for a cow, and a little Wi-Fi ID tag is 50 euros. So you basically spend your money on a bunch of access points on a field with solar panels, and then you put a Wi-Fi RFID tag, and there you go. You have it for 1/3 of the price. The scientist was really pleased with that. Many rogue, yes. Voila, that's the end of the presentation. Thank you very much.
Thank you, Philippe. I guess this is what you get when you put a zoologist in charge of your wireless LAN deployment. You get Wi-Fi cows and Octopus software. Let's say 1 or 2 questions still for Philippe. Anyone? Andrew, over there.
I'm okay if you've said the question again. It was simple. Is the software available, going to be available?
Yeah.
The question is the software going to be available, and if yes, in what form?
That's a tough question. We have been debating about that, and the problem is the support. So we may do the equivalent of Radiator, basically a very affordable software, so that we can keep funding the developers, because the guy who wrote that is really talented, but I don't think he will stay on a graduate assistant salary. So.
Thank you again, Philippe. Oh, is there another question up there? Oh, sorry. One more question.
So it seems to be a very nice software, but as you mentioned, it's proprietary at the moment. Do you have any plan maybe to go to standardization bodies, and why not trying to standardize the way you are doing it, like IETF or something else?
No, the software uses only standard things. You know, it runs on any operating system. It's written in Perl. It's PHP, Apache, so you can run on Windows and MySQL. So, and we made sure that we didn't make a single system call, so that you're completely OS agnostic. Now,
but to discuss with the devices, there are different
yes.
vendors.
By the way, it is standard. I'm not planning to go to the IETF to propose a software, but we have a compatibility matrix in the software where you can support any style of access point, putting your SNMP community, your SNMP, your MIBs in. And so you have one criteria, you ask for the criteria, and the compatibility matrix returns to you the way of talking to that style of access point.
Okay, thank you.
Okay, then thank you again, Philippe. One last applause for Philippe. So now we're slowly retracting onto the wired network. We went from wireless spectrum to management of access point, and now we're going to move even further back. Kostas Kalevras of the National Technological University of Athens is going to talk to us about his experience with scaling radius to large-scale deployments. And Kostas is really the right person to talk about this, because he is managing the LDAP and radius deployment for the Greek school network, and is also one of the main developers of the free radius software. So I think we are going to have a very interesting talk from Kostas.
Thank you. I guess, okay.
Now, my talk will not have much to do with wireless networking. It's mainly focused on radius applications. It will consist of... Excuse me? Now?
Yeah, it's okay. Can you...
Oh.
Here it would be great.
Okay. Can you hear me better now? No. Serious? Okay, yeah. Now, the presentation will be of two parts. The first one will be general guidelines on scaling radius services. And the second part will be a case study of the Greek school network and how we, the steps we took to increase the scalability and performance of the radius service. Now, in general, radius protocol is still used in wireless hotspots, for network authentication, and mainly for dial-up and DSL broadband access. And in sometimes, like in my next presentation on PGNA, for AAA for services. Now, why do we need high performance? The first reason is that the user population is increasing all the time. The other reason is that we have some new developments like authenticating schools and things like that that usually need a lot of authentication requests to get in the network and also only stay online for a few minutes and then go back on, except if we are dealing with always-on access, which is not the case in Greece. Now, the key issues in scaling the radius performance, mostly it's about redundancy, coupled with failover with full accounting, and all this always with double again detection. That will give us high availability and will allow us to spread the load between a lot of radio servers so that we don't keep all the traffic on one and only. This has two main steps. One, having a scalable and replicated user database like SQL or LDAP, and the other, to have an equally scalable accounting infrastructure, which is usually based on SQL. We also need to be able to accommodate for encrypted authentication requests, like EAP, TTLS, TLS, PAP, all these new protocols. And all this with ease of server maintenance and be able to delegate the administration. The two main guidelines are that accounting is more important than authentication, and it can get very large. And the other is that we should not use a single server, but we should distribute the load and replicate all data. That will allow us to have reliability and scalability. I have a large availability for our service. That's how we have created the service in the Greek school network. It constitutes of two radio servers, one for the north of Greece and the other for the south of Greece. They both have fully replicated accounting so that we can have double login detection for the whole country. The accounting is replicated by a certain process running on each radio server. And each of these radio server has a dedicated LDAP server, which also has replicated user data. And the access servers, depending on which side of the country they are, will have as primary one of the radio servers and then secondary the other. And that can scale to much more high numbers. The other is quite normal to tune the SQL accounting, like indexing fields, spreading the load between multiple server threads and not serializing our accounting, and to use a connection pool instead of making a connection to the SQL database on its request. Now, for the user database, we need a high-performance database like SQL or LDAP. In our case, we are using SURN1 directory server. That will mean that we have ease of administration since we use protocols like LDAP, which provide certain means to delegate and make our lives easier when administrating users. And we need to configure replication so that ideally each ready server will have its own dedicated user authentication server, well, authentication database. Another guideline which we have found to be quite of good performance is to only service live requests. That is, keep on memory a table with only the online users and use an on-disk buffer to put the accounting data and then through a separate process send them on to the accounting database for permanent storage. This will guarantee us a low service time because the time for writing things on a detailed file on the disk and on the on-memory table is quite small. And we can also perform complex operations like statistics generation online instead of performing it in a batch way, sometimes at night. And another thing is to keep as much of the server configuration in a database instead of text files, like the client configuration and the real configuration. That can give us ease of administration, which can be done through a web interface, probably even with authenticated access. We don't need to provide access to the radio servers for anyone needing to perform these tasks. We can delegate the administration. In Greece, we have each university handles a small part of the country, and we have 12 universities delegating the administration. And a last point is that we have a single point of administration, and we can automate the procedure of all the above configurations. Now, in our case, it's the Greek school network with 52 access servers, around 5,000 schools, 50,000 lab accounts, and we have around 100,000 sessions per day. The authentication database is an LDAP with 2 fully replicated LDAP servers. Now, what we choose as a radio solution was free radios. The reason for that was that it was scalable, multi-threaded, and is in active development. That's not the case with most of the open source flavors of radio servers. It's open source. That was another good thing, instead of keeping to a vendor, which in the case of LDAP, in some cases is not so good, especially if you're waiting for a bug fix or things like that. And we also participate in the server development, so fixing bugs is mainly opening the source code and fixing it ourselves. And it supported all the features we wanted, like LDAP authentication, SQL database support for all the app types, and things like that. Now, the 3 scaling steps we took, apart from the guidelines I outlined, were pre-authentication, a new server structure, and a caching module. Pre-authentication is mainly on call setup for the dial-up connection. The access server will send the caller ID of the calling station, and we will perform authentication based on that only, instead of having to go through an authentication process with username and password. That will give us a lower overhead, and it will reject the call on call setup, which means that no additional phone costs will be required. We can lock a user and he will not be able to even make a phone call, and will not have to pay anything for that. The new server structure is mainly the idea of the live request table. We maintain a non-memory live accounting table, and permanent accounting is performed by a separate process. We have two processors on each ready server, one storing data on the local database server and the other one storing data on the replicated backup ready server. The main advantages for that are that we have a lower and guaranteed accounting service time, and that we can perform statistics generation online in real time. That was a major step because previously we had to make statistics generation in the night, and that would create problems on the radio service, since the statistics were created on the same table where we store accounting. There's also a caching module, which will cache the server response based on a configurable key. What we achieve from that is lower service time, and if we combine it with pre-authentication, where the incoming request is almost the same every time, we can make the key to be the caller ID. We can service almost all the requests from our cache and not from the LDAP service, so no queries are performed there, and we have a lower service time. The one disadvantage is that cache entries must be erased when we change a user entry. That is a tricky part, but we have a solution which will require signaling the radio server each time we change the user. Now, the conclusions are that Redis is still at the core of AAA infrastructure. It can, based on our experience, it can still scale to accommodate current and future needs. And it's been used with success in large-scale installations. And that's my presentation. I think that was it.
Thank you, Kostas. We have room for a number of questions, actually. This is the first speaker who's really very well on time. So, who has a question? Well, the microphone will take some time, but it's coming. Go, 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 go.
What is your experience with the free radius authenticating, let's say, Microsoft clients, which are very specific and sometimes force you in taking Microsoft-specific platform?
Well, in general, there's no real problem. Apart from certain versions of PayApp, where even there things go smoothly, especially in the latest versions. So there won't be any real problems.
Thanks, Andrew Cormack, Ukerna. So I've just been looking for the reference and I can't find it, but you said that radius accounting was actually more important than authentication.
Based on our experience.
which was the opposite decision we came to. There was a paper that raised concerns about radius accounting where you were running radius packets across multiple admin domains because it was UDP and you could therefore insert accounting, you could insert session start, session stop.
You're talking about proxying though, right? That's a proxy installation where I guess you have to send it through multiple proxy radios.
Yep.
Well, in our case, it's just a radio
You're
service.
not doing proxy. Okay, that's the difference. It was in the eduroam context. So, yes, that's the difference. Thank you.
Okay.
You mentioned that one of your decision criteria that you are part of the development team. Would it have been different if it was not the case to use free radius?
Well, we started using it without me being in the development team. I just got in because I needed to fix a few things. Even when we started using it, which was around 3 or 4 years ago, it was still at the lead of open source solutions. Radiator was much better then. But I think it would go. There are other people involved who make a lot of code changes, so it would go even if we weren't involved in the development.
Any other question?
Since we have the time, I thought I could try to learn something. How often did you have to use the failover, the secondary radius server? Can you give us some idea of? You read all the time on the internet that radius is not very, it has problems with stability. And what is your experience with that?
There are times when one access server will try using the other radius server because there was a few timeouts in the UDP packets. But in the case of the radius server itself, it is quite stable.
Is that the experience that people here in the audience also have? I'm interested because we are testing radius, but we haven't really deployed it. So
I see lots of people who want to comment on that. First, I'll do the microphone as well then.
Well, Stefan Winter from Luxembourg, the NRAN in Luxembourg. We are using FreeRadius as a top-level server for our eduroam domain, and it's running since months, quite good. And we're using it for radius accounting since years with our post and telecom in the country. And we haven't seen many outages, so I can say it's really quite stable, yes.
Then Dubrovko wants to say something about the Navis radio server, perhaps?
Thank you. Dubravko Penzic from University Computer Center in Zagreb, Croatia. We have top-level radio server based on the Navis Radius server. Have 3 times more AI requests per day, so 300,000, and we have 2 radio server and only less than 1% of request was sent to second radio server. So it's very, very stable.
I can add to that we use Radiator in the Netherlands and we see similar numbers. If it is higher than a couple of percent, it's usually because we did something terribly wrong.
Let me just add that usually the authentication of the accounting database will go down, not the radio service.
Anyone else? Last chance? Then once again, Kostas, thank you very much. Thank you all very much for attending. The next session here will look a bit further ahead. We'll look into IPv6 and other alternatives for radius. So I hope to see you again after the break. And I would like one more applause for all the speakers in this session.